Welcome to Thermochemistry Lecture A. Today I'd like to talk to you about heating and cooling curves and how to do calculations using segments of the heating curve. If we take a look at this heating curve, what this assumes is that we've started off with a sample as a solid that is below its freezing point. And as time goes by, we are adding heat. So even though time is the x-axis, we can assume that we're adding heat if we're reading it from left to right. If we're reading it from right to left, we can assume that the heat is being removed. On the y-axis, you'll notice that it reflects some temperature changes. So if I were to label these axes, I'll call this first line segment here, AB, we can see that we have a solid below its freezing point. And as we heat it, you can see that the average kinetic energy, or the temperature, increases. Then if I examine line segment BC, you can see that we have achieved melting, and we're making that phase change between solid and liquid. And so during that plateau, if you will, we do not have an increase in temperature, but we are transitioning from solid to liquid. So during line segment BC, we have solid and liquid at the same time. During line segment B, or during point B, it's completely solid, and during point C, it's completely a liquid. Then if I examine line segment CD, you can see that I have a liquid and that its temperature is increasing. And you can see that once I reach D, I'm going to start boiling or evaporating, or if you will, generically speaking, we call this change vaporization. And you can see that during line segment D, we have a pure liquid, and during point E, we have a pure gas. Then if I look at line segment EF, you can see that we're heating the gas beyond its boiling point. So as we start to consider some calculations and how we would go about calculating the amounts of heat that we would add, during any line segment that has an increase in temperature, we would use this first equation. Q equals MC delta T, or sometimes we call it MCAT. And the M, as you can see, stands for mass. The C stands for specific heat capacity, which is a quantity that's specific to each individual substance. And delta T is change in temperature. So during line segments AB, CD, and EF, anything that has that diagonal increase indicates that it has a change in temperature, so we can use MCAT for those line segments. If I examine line segment BC, what we know is that is melting. And I will tell you that heat of fusion is used when we would like to talk about melting a substance. And if I look at line segment DE, I would use heat of vaporization. And that is when we are concerning ourselves with vaporizing or boiling, in other words, that liquid to gas transition. So these are all the equations that we would use. We said we're going to use heat of fusion during line segment BC, and we would use heat of vaporization during line segment DE. If I consider what determining freezing point would look like in the lab, we can see that the student has something referred to as paradichlorobenzene, and it is a liquid above its freezing point. And they take data, as you can see, for 10 minutes. And what you might notice is that that temperature 53 repeats itself several times. Consider what this might look like if I had that same set of axes that we were just using, where I were to consider time. Now this time we are removing heat. And you can see that we said this substance is a liquid at the very beginning, degrees Celsius, and it started off at 65. And you can see that initially it has that decline, and it reaches 53, and you'll see that it repeats itself several times. So 53 is going to give you that plateau as time goes by. You've got several readings at 53, and then it continues to decline down to 42. And what you might notice is that this looks very similar in shape to our heating curve. It's just red in reverse. It starts off high and it gets low. So from 65 to 53, we have that substance completely in the liquid phase. From 53 to 42, it's completely in the solid phase. At this point, it's a pure liquid. At this point, it's a pure solid. And in between, it's a blend of the two. So thermochemistry is all about studying heat, which is, of course, a form of energy. We've spoken about heat briefly in the past. It's measured in joules, and you'll find that on the front cover of your reference table. There is a such thing referred to as the law of conservation of energy. You're like, sounds like the law of conservation of mass, law of conservation of charge. Yes, this is the third piece of our conservation laws. The law of conservation of energy states we cannot create or destroy energy, but we can transfer it. So how is heat energy transferred? It flows from the hot object to the cold object, and hopefully you know that. In other words, when we put an ice cube into a glass of water, the heat flows from the water to the ice cube. In other words, you can't have cold transferred, or cold doesn't flow, but heat does flow. So it would go from the water to the ice. We also cannot measure joules directly. I don't have a device that I can put in a substance and measure how much heat it has, but what we can do is track temperature change. And if we can measure a temperature change, then we can calculate heat using MCAT. So as we said, heat is something that in theory we can measure using a calorimeter. And I'm not sure how good you are at your Latin-based languages, but I think calor means heat in some degree. So it's measuring heat. And again, we're not measuring heat directly. What we are doing is putting this chamber in some water and tracking that temperature change of the water. And we know that whatever lost the heat is going to gain the heat. And as we said, we cannot lose any heat. So whatever energy is released, that cooler object is going to absorb it. So let's take a look back at our MCAT calculations. If I were to examine some practice problems, how many joules are absorbed by 100 grams of water in a calorimeter if the temperature of the water increases from 20 degrees Celsius to 50 degrees Celsius? Because we have a temperature change, we can use MCAT all the way. But because we are in Honors Chem, we use dimensional analysis. So what are we going to start with? We're going to start with the constant. Why are we going to start with the constant? Because it has the most units. So take a look. 4.18 joules per gram degree Celsius. I like to call that JGOX. So I'm going to start with my constant, 4.18 JGOX, and I'm going to make it look like dimensional analysis with a numerator and a denominator. There we go, JGOX. And what we need to know, of course, is that degrees Celsius doesn't represent an absolute temperature, but rather it represents a change in temperature. So we are looking to keep joules. So we will cancel out grams with the mass, 100 grams of water. And we will cancel out our delta T. The difference between 20 and 50 degrees Celsius is 30 degrees Celsius. And so that will cancel out our grams, as we said. And this is going to cancel out our delta T right there, our degrees Celsius. And if I go ahead and push buttons, I was given 3 significant figures. I'll give back 3. So it's about 12,500 joules. Now, usually we end up having a lot of heat. So kilojoules is a definite thing. So you'll probably want to get really good at sliding your decimal place back and forth 3 places. So this is also 12.5 kilojoules. So that was solving for joules. Now let's try to solve for mass. Again, if I start with my constant, 4.18 JGOX, I want to end up with mass. So I want mass over 1, or mass in the numerator. I don't want it in the denominator. In other words, I don't want inverse grams. So I'm going to take my constant and I'm going to invert it. 4.18 JGOX inverted looks just like this. And I was given 500 joules of energy. So this time my joules is going to cancel here and here. And I'm looking to keep mass, and I want to cancel degrees Celsius with my temperature change. My temperature change from 25 to 50 is a difference of 25 degrees Celsius. And so that's going to cancel out my degrees Celsius here, top and bottom, as my delta T. And I can push buttons, and I get 4.8 grams. Next example, we'll solve for the other variable. Our third variable we want to know about, temperature. So here we go. You can probably imagine, again, we want degrees Celsius. We don't want inverse degrees Celsius. So once again, we're going to flip our constant. So we're going to run it as gram degrees Celsius. So I can solve for my degrees Celsius, and my 4.18 joules goes on the bottom. So my joules is going to cancel my 1,000 that was given. And my 50 grams as my mass is going to cancel. And what you see we have left is my degrees Celsius. That's all I have left. My grams canceled, my joules canceled, and I have left my degrees Celsius. So when I go ahead and push buttons there, I get 4.78 degrees Celsius. So the question is, am I done with this problem? And the answer is certainly not. What I just calculated here at 4.78 degrees Celsius is a change in temperature, not an absolute temperature, but rather a change in temperature. So you can see that we started off at 20 degrees. And of course, what's going to happen? I'm going to go up from 20 or down from 20 by 4.78 degrees. So when it tells me that I'm absorbing the heat, it would stand to reason that it's going to get hotter, so therefore the temperature is going to go up. So I add my 4.78 degrees Celsius to that 20 degrees Celsius, and I get my 24.78 degrees Celsius as my final answer. So we had a chance to solve for all of the terms. We solved for joules, we solved for mass, and we solve for delta T. So now let's take a look at specific heat capacity. What you might notice is that specific heat capacity in our reference tables, it's very specific for liquid water. Well, guess what? Specific heat capacity is something that is a constant for each individual substance known to man. So it would be something that we would have to look up in a reference table if it were not liquid water. So you can see that the specific heat capacities vary. Water, as we know, 4.18, here they give it to you a little bit more significant figures here. Water, liquid water is extremely high. So what that simply means is the fact that water can take on a lot of heat, or it has a high heat capacity before it changes its temperature. And I know because I spend a lot of money on heat for my pool before I get any chance to get a temperature increase. Whereas if I look at a cooking pan, if I have a cooking pan made out of copper, I want it to increase its temperature rapidly. So you can see that copper has very little heat capacity before it starts to change its temperature. So you see that most metals there tend to be less than 1. So the fact that water happens to have such a huge number is quite remarkable. So we have done calculations using JGOX already, joules per gram degree Celsius. But in higher level chem, of course, we know that the mole is the great equalizer. So there is also sometimes molar heat capacity. So that would be in joules per mole degrees Celsius, or JMolx, if you will. Now I want to take a moment and talk to you about a delta T in Celsius and a delta T in Kelvin. And I just want to prove to you something for just a moment. If we consider the boiling point of water, and I'm pretty sure that we know what it is, that it is 100 degrees Celsius. And if I want to consider the freezing point of water, what we know is it's 0 degrees Celsius. Now, if I can convert both of these into Kelvin, I know that table T tells me how to do that. I add 273. So in Kelvin, 100 degrees Celsius is 373 Kelvin. And when I add 273 to 0, we can see that our freezing point of water is 273 Kelvin. So now what does that mean? In this unit, the change in temperature is the star of the show. So I want to prove to you here that a delta T in Celsius and a delta T in Kelvin are the exact same thing. So all of these units, I read them as JGOC as kind of a joke because joules per gram degree Celsius and joules per gram Kelvin are the same thing. So I can call it JGOC and it works for both, or JMolk works for both. So I know that our delta T in Celsius and delta T in Kelvin are the exact same thing. So let's take a look at a substance that's other than water. If I have 4 grams of glass and I'm heating it from 274 to 314 and it's found to absorb 32 joules, find the specific heat of the glass sample or specific heat capacity. Sometimes that word capacity gets dropped. So let me write myself a goal. I'm looking for JGOCs, joules per gram Kelvin. And so this is sort of a new dimensional analysis skill for us. We have started with the constant because it had the most units, and we've knocked out what we don't need. However, there's another side to that story. I can also write myself a goal and build it up to make a constant. I can see that joules is going to go in my numerator, so I'm going to pluck that right out of the given information. Grams needs to go in my denominator, so I'm going to pluck that right out of my given information. And I also have Kelvin that needs to go in my denominator. So I can see that, oops, this is not K, this is joules. I also need Kelvin in my denominator, and we know that that represents a delta T. So the difference between 274 and 314 is 40 Kelvin degrees, or just 40 Kelvin. So when I push my buttons, check out what I end up with, joules per gram Kelvin, JGOCs. So not only can I take a constant and knock it down, I can also take a bunch of little pieces and build it up to make a constant. So this ends up being, when I push my buttons, it ends up being 0.2 JGOCs. And that is that specific heat capacity of that glass sample. So now that we have the specific heat capacity, we'd like to see if I heat the sample, how much energy is required. So I'm going to start with my constant this time because it has the most units and I want to knock down what I don't want. I want to keep joules and get rid of grams and Kelvin. So I can see that our glass sample was 4 grams from the initial premise. So that's going to cancel my grams. And it also started at, it was at 314 now. And I want to continue heating it up to 344 from 314. So I can see that the difference there is going to be 30 Kelvin degrees, or 30 Kelvin. And that's going to cancel my Kelvin. So I go ahead and push buttons there, and I end up with about 24 joules of heat is required to make that temperature change. So let's take a look at a molar heat capacity example, since I promised you that's a thing. And we can see that I've got gold this time. How awesome is that? And we're given the fact that it's 25.4 JMolks. I've got 200 grams at 20 degrees, and I want to know its final temperature. So when I consider J molks, I need final temperature. So it's definitely the Kelvin that I'm going to be interested in. So I'm going to need to take that constant. Let me write it so you can see it, dimensional analysis style. 25.4 J molks. And you can see that we're interested in final temperature. So we're definitely going to be solving for Kelvin, which we can see is in the denominator. So I'm going to want to take that constant and invert it so that my Kelvin ends up in the numerator. So I'm going to keep my Kelvin. I can quickly cancel out my joules with my 2.5 kilojoules. We mentioned getting really good at sliding the decimal place 3 places one way or the other. So I can see that that is 2,500 joules. And so that's going to cancel my joules here and here. And I know that all I want to keep is Kelvin, so I've got to get rid of moles. And as we know, this is gold specifically. Moles of gold. I'm not given moles of gold, I'm given grams of gold. So what do I need to do to get to grams? I need to make a conversion factor. Oh, look at that. That looks like molar mass. So if I look up the molar mass of gold, it is 197. That's going to cancel my moles. And now I can cancel grams with the mass that was given, which is 200 grams. So that's going to cancel here and here. And now, truth be told, this 200 grams, I could have quite easily put this 200 grams in this spot right here, and it would have been perfectly fine. It's just that you guys aren't used to seeing it that way, so I just expanded it outward a little bit. But in the future, you might see me put things in that empty space and just to fill it up. So I don't use so much space. So I go ahead and push buttons, and this is 97K. And now what we know about that is that it is not our final temperature. 97K represents the change in temperature. It started off at 20 degrees Celsius, and it went up by 97K. As we said, a delta T in Celsius and a delta T in Kelvin is the same thing. So if the temperature increase was 97K, it was also 97 degrees Celsius. So my new temperature, it absorbed heat, so it went up from 20 by 97 degrees, and so my new temperature is 117 degrees Celsius. So all of this was fine and well, and we talked about a lot of different temperature changes. So now let's talk about those plateaus of the curve, the phase changes, if you will. During a phase change, you can probably imagine the solid has a crystal lattice, whereas the liquid, things are a bit more free-flowing. So during that phase change, particles get rearranged, and that causes a change in their potential energy because they have different positions. So there's no change in average kinetic energy, which is energy of motion. Their temperature stays the same. So that first plateau, or the plateau at the lower temperature, is referred to as heat of fusion, as we said earlier. It is the energy you need to melt a substance at its melting point. So you need to be at that 0 degrees Celsius if you're talking about melting ice. And heat of vaporization is the same thing, but for vaporization. And what you might notice is that the heat of fusion's line segment, that line segment here, compared to the heat of vaporization, this guy's line segment right here, you can imagine it takes a whole lot more energy to pull the particles of a liquid so far apart to a gas. In other words, break their intermolecular forces or their bonds of attraction to pull them so far apart that you make a gas. Whereas just going from solid to liquid, they don't have to be pulled apart that far. So as I consider doing some calculations with this heat, How much energy do I need to perform the following change at 273 Kelvin? So what I can see is, of course, 273 Kelvin. If I subtract 273, that's 0 degrees Celsius. So I am looking to melt ice at its melting point. So I need to pick out a constant to use. Since I no longer have a delta T, MCAT is not going to be in play. So I have my two phase change equations to choose from, and so this one is going to be heat of fusion. So fusion is our F word for melting. So I'm going to choose that constant at 334 joules per gram. Since I'm solving for joules, I'm going to run that constant as it is, and I have a 100 gram sample. So grams are going to cancel there and there, and I get 33,400 joules. And as we said, usually we end up using a lot of heat. We have a lot of heat, so that's also known as 33.4 kilojoules. Second example, this time we're looking at vaporization. That same 100 gram sample is now at 373 Kelvin. If I subtract 273, you can see that that's at its boiling point. So we are looking to vaporize liquid water to a gas. And so I need heat of vaporization this time. And I'm going to start with that constant for heat of vaporization is 2260 joules per gram. I'm going to solve for joules, multiply that by our 100 gram sample, and I get 226,000 joules roughly. And so again, that's a big number, so let's make that into kilojoules. That's 226 kilojoules if I slide it to the left. So let's talk about how we might get the heat of fusion in a lab experiment. If I started off with an initial volume of water that is 100 degrees Celsius, you might recall from earlier in the school year that when you have 1 milliliter of water, you also have 1 cubic centimeter of water. But we're not interested in that right now. For water, if I have 100 milliliters of water, I have 100 grams of water. And at the end, if I have 156.1 milliliters of water, I have 156.1 grams of water. So what I'm looking to calculate, if you remember heat of fusion from our previous reference table, the units are joules per gram. So let's take a look at how that might come into play. We are looking for joules per gram, as we said. So what are we doing? To do heat of fusion, we have to be able to melt some ice. So we have our water's mass is 100 grams. That's our pure water mass. Let me write it right down here. Our pure water mass is 100 grams. And I put some ice in it, and you can see the ice melted. And my final volume of water after the ice melted is 156.1 milliliters or grams. So by subtraction, it would make sense that whatever ice melted, the ice that melted, its mass is equal to the difference, which is 56.1 grams. And of course, we're always interested in a delta T. So hopefully we can see once I put ice in my water, you can see that, of course, the water cooled down. And if I take the difference between the two, I can see that my delta T here is 49.9 degrees Celsius. So back to our original goal. We're looking to get joules of heat. Now, which way did the heat flow again? We know if I've got ice water, it's going to be joules of heat that's transferred from the water. And the grams is going to be the grams of ice that actually melted. So that is our goal. So how am I going to go about achieving that goal? I know that I had a temperature change, so I can use MCAT, or starting with the specific heat capacity of water. Remember, this is joules transferred from our liquid water to the ice. So 4.18 JGOX is the specific heat capacity for that liquid water. As you see, we had 100 grams of that liquid water that transferred the heat, and it caused a delta T of 49.9 degrees Celsius. So at this moment in time, I have my numerator all set. I have my joules ready to go, and all I need to do is put it over the grams of ice that melted. Well, we can get that guy straight out of our data table right there. We've got 56.1 grams of ice that melted, as we said, and I've got my goal accomplished. Joules of heat transferred from the liquid water to the ice over grams of ice melted. And I push buttons there and I get 372 joules per gram. And of course, we saw earlier our accepted value is 334, so we didn't do too terribly bad. Let's consider our heating curve when we have to use multiple segments of our heating curve. We have a story here. We want to calculate how much heat is required to bring 15 grams of water at -4 degrees Celsius to 95 degrees Celsius. So as time goes by, I'm looking to go from -4 degrees Celsius to 95 degrees Celsius. Let's sketch out what's going to occur. If I consider this is water at -4 degrees Celsius, we know this is ice. So this is a solid below its melting point. And we know that its melting point is 0. So what has to happen? I have to heat up the ice from -4 to 0. And what's going to happen? Just like when we saw this earlier, when we have the phase change experimentally, what's going to happen? I'm going to get that same temperature several times in a row, and I'm going to get a plateau. The only difference is up here, I was calculating freezing point, and down here, I'm going to look to show melting point. So my ice is going to melt for a bit, and there's my plateau. And then at one point, it'll be completely liquid water, and I want to continue to raise it until it's 95 degrees Celsius. So what you might notice is that my heating curve involves 3 different line segments. I have to do 3 things. I have to heat the ice, and I have to melt the ice, and then I have to heat the water. And so to calculate this heat, all I need to do is do these 3 calculations and add them up, and I'll be able to get the heat total that was required. So let's go about doing that. So here's the thing. Specific heat capacity at 4.18 is only good for liquid water. So if I slide back up a little bit, you can see that liquid water and ice have 2 completely different specific heat capacities. Here is our specific heat capacity for ice. So that's what I have to do when I'm in this line segment for heating my ice. I have to use that 2.03 degrees Celsius that you saw there, or gram degrees Celsius, because joules per gram degree Celsius, that is, because that's the specific heat capacity for ice. Each substance has its own. So I had 15 grams of ice, and I'm going from -4 up to 0 degrees Celsius. At that point, it stops being ice. So I push my buttons here, and this works out to be about 121.8 joules. Now I need to do the phase change melting. And I use my heat of fusion, 334 joules per gram times 15 grams. Notice that there's no delta T. We're staying at 0. We're plateaued. So when I push those buttons, this guy ends up as 5010 joules. And so I'm now at this moment in time. So now I need to go from X to the top, where I'm going to heat liquid water from 0 up to 95. And so now I can use liquid water's specific heat capacity at my 4.18 JGOX. Still have 15 grams. And I'm looking to go from 0 to 95. So a delta T of 95 degrees Celsius brings me to, 56.5 joules. So if I add together my 3 segments of my heating curve, I get a total value of 11,148.3 joules. Wow, that's a lot of significant figures, and it's also a large number. So he said to get used to using kilojoules a bit. So let me knock down a few significant figures there. I was given 2, so I'll give back 2. So this is about 11 kilojoules of heat required for that. Let's look at a backwards example. This time, let's do a cooling curve. So we're looking to take some steam at 104 degrees Celsius, and I want to bring it down to 58 degrees Celsius. So I'm going to go from 104. It's going to get cooled. Cool until it reaches 100. And now instead of vaporizing, this time we're going to do the reverse, which is condensing. And guess what? Condensation is just simply reverse vaporization. So the magnitude of heat of vaporization at 2260 joules per gram is still going to stay, but the direction changes. So instead of adding it, we're removing it. And then we're going to continue to cool the water from 100 down to 58 degrees Celsius. So hopefully you can see this time, again, we have 3 line segments. I need to cool my steam. So there is a delta T there. I need to condense the steam to liquid water, and I need to cool that liquid water. So again, 3 segments of the curve. If I were to continue going downward, let's take it all the way down to, instead of 58, let's take it down to 0 degrees Celsius. So let's say I want to have ice. Let's cool it to ice at 0 degrees Celsius. Cooled to ice at 0 degrees Celsius. That'll be much more fun. So instead of 58, I'm going to go all the way down to 0. And if you notice, it said we want to have ice. So at this moment in time, right here, I have liquid water at 0 degrees Celsius. I want to have ice at 0 degrees Celsius. So I need that very last little segment, and at this blue spot right here, that's going to be ice at 0 degrees Celsius. So I have one more segment that I have to do. I have to be able to, after I cool the water, I have to be able to freeze that liquid water into ice. And again, as we said, if condensation is reverse vaporization, then freezing is reverse fusion. But the numbers are all the same. So let's look at our first piece, cooling steam. As you may have guessed, there is, of course, a delta T. And so they gave us our specific heat capacity of steam. It is not the same as liquid water. It is 2.08 JGOC. You might notice that specific heat capacity of ice and steam are very similar. So we had a 50-gram sample, and we are cooling it by 4 Kelvin degrees. Remember, specific heat, a delta T in Celsius and a delta T in Kelvin are the same thing. So this works out to be 416 joules, and that was the first segment of our plan. Now we need to do reverse vaporization. We said the magnitude was exactly the same. It's still 2260 joules per gram. I still have 50 grams, and there's still no delta T. So this is 113,000 joules. That's a lot. So that's piece 2 of our plan. Now I need to cool that liquid water from 100 down to 0. So since I have liquid water at this moment, I can use my 4.18 JGOX. I still have 50 grams. And my degrees Celsius, or my delta T this time, again, delta T in Celsius, delta T in Kelvin, same thing. It is 100 degrees Celsius. So here, cooling that water would cause 20,900 joules of heat to be removed. That's segment 3. The very last portion of my program is to freeze. So we said freezing is reverse fusion. The magnitude is still the same, it's just the direction that changes. 334 joules per gram still holds up, and I still have my 50 grams. I've got my heat, I've got my mass, again, no delta T. And so the heat of fusion, in order to freeze that ice, would cause 16,700 joules of heat to be removed. And I add together my 4 segments. These 4 segments add up to roughly 151,000 joules, or as we said, that's a big number, so 151 kilojoules will suffice very nicely. That's all I have for Thermochemistry Lecture A. I hope you enjoyed it and have a great day.